Hi, I'm Caleb, and today we'll be building a power supply system I made for my bicycle. This spring, I designed a safety and control system that includes a set of handlebar lights to illuminate the road, as well as a Raspberry Pi with a cellular connection, light sensor, and accelerometer to determine when to turn the lights on and off. That project was software-based, and in order to take it actually on the road, I need a reliable power supply system. An inexpensive solar panel charges a 3.7 volt battery, but my LEDs need 12 volts, and my Raspberry Pi needs 5 volts. Therefore, I designed a boost converter for the 12 volt supply and bought an off-the-shelf buck converter to step that down to 5 volts. Let's check it out! First, the bad news. My bicycle is at home in Massachusetts, and for some reason, the Amtrak Northeast Regional line doesn't allow you to take bikes on the train. So I'll have to wait till the next time my parents come to New York to demonstrate this on my actual vehicle. Fortunately, I scavenged through my room and found a light strip identical to the one that I have on my bike, so we can use this to test. The second piece of bad news is that the solar panel sold by Adafruit and the solar battery charger, also sold by Adafruit, are not compatible. What the heck? Therefore, we'll have to use this standard DC power supply to test our equipment until the adapter cable arrives. We first implement the circuit to provide control for our converter. We're using a 555 timer, shown here under this mess of wires. The 555 is apparently the most popular integrated circuit ever sold, and it's easy to understand why. With simple RC feedback, you can produce pretty much any frequency and duty cycle you could want. In the previous report, we calculated that we would need 100 kHz and 70% duty cycle. As the TI pointed out, the ripple would be too high in the case where our bicycle LEDs are off, so we've increased the frequency to 160 kHz, as you can see here. The duty cycle is 67%, and we'll see if that's good enough when we test out the rest of the system. Next, we build our boost converter, as you can see here. Inductor, switch, diode, and capacitor. We are expecting several amps of current, and PCB traces have a limited capacity. For example, these 10 mil traces can only handle about 1.5 amps. Therefore, for safety, we've connected many wires in parallel to ensure that we can carry the current we need. This is pretty silly, so in the final PCB we will just use big traces. Now we've connected our LED strip, and we're going to try controlling this thing with an ideal waveform generator instead of our 555, just to make sure we get each component working separately first. I'll turn on the 3.7 volt power supply. No light yet. Now let's turn on our control signal. The lights seem to work, but our output waveform is crazy. That's not 12 volts constant. As it turns out, I hadn't soldered this capacitor correctly. How foolish. Having resoldered the pesky capacitor, things seem to be working now. Our average output voltage is 12.7 volts. I've zoomed way in so we can clearly see the voltage ripple, and according to the scope, this is about 100 millivolts, which is less than 1%. Great! Now let's try connecting our 555 control circuit. Still works. Let's check out our output voltage. It's about 11 volts, which is a little low. We could fix that by changing the feedback resistors in the 555 to increase our duty cycle. Our output ripple is also a little high. 300 millivolts is about 3% of 11 volts. We could fix this by adding a larger capacitor to the output. We still need to be able to power our Raspberry Pi, which takes 5 volts input. Shown here is our off-the-shelf buck converter, which will take our 12 volt output and step it down to 5 volts. Let's see if it works with the LED strip too. LEDs are still on. Let's check out our output voltages. We've scoped both of them. On channel 1 in yellow, you can see we've still got our 11 volt output voltage of the boost converter. And on channel 2, we can see the output voltage of the off-the-shelf buck converter is 4.8 volts. Time to see if it works with the actual Pi. It works. Excellent. The Pi and the LEDs both stay on, which means we are good to go. Let's check out our power consumption to see what current the Pi actually draws. The input current is 0.62 amps, which means our power consumption is 2.3 watts. With the LEDs only, we consumed 1.9 watts. This means that the Raspberry Pi consumes 0.4 watts at 5 volts, or only 80 milliamps of current. The 1 amp power supply requirement is super conservative. The reason that they make this requirement conservative is likely that the company expects us to use peripherals like a keyboard and mouse with our small computer. However, when we take this thing on the road, we'll only be using a few low power sensors, and our cellular module even has its own battery, so we'll be just fine. In summary, I designed a system to provide 2 voltage outputs for my bicycle safety and control system. The heart of this is a boost converter that I designed to convert my 3.7 volt solar panel battery voltage to 12 volts needed by the LEDs. I also used an off-the-shelf buck converter to step down the 12 volts to the 5 volts needed by the Raspberry Pi. We tested out the operation and determined that the output voltage is closer to 11 volts rather than 12. Therefore, an obvious next step is to change the duty cycle of the 555 timer to get the voltage that we want. As we mentioned earlier, another obvious next step is to increase the output capacitance in order to lower the ripple. We'd also like to charge our solar panel once we get the adapter cable that we need for that, so that we can make sure this thing works with the solar panel included. Finally, we'd like to design a nice PCB so that we can get rid of its rasnets. Thanks for watching. Another next step is to clean up the huge mess I made.